Hey, this video is going to talk about general engine measurements for Math 8521. Nothing too insane here, but good to know some lingo and how to do some simple math. So what we're going to look at are cylinder taper, out of round, camshaft lobe height or lobe lift, rocker arm ratio, and finally valve lift. Starting with taper, so what we're looking at here in this picture is the cross section of a cylinder. So let's say, if we were to see it in more 3D, it might look something like this, where up here we have the deck, here's the cylinder itself, and then down at the bottom somewhere we got a little crankshaft doing its magic, that kind of stuff. Okay, just to get ourselves located in the cylinder. So what we see happening is two measurements, A at the top and B at the bottom. And you can tell from the picture that A has a bigger diameter than B. And what that represents is taper. And taper is the wear that you get from the top, at the top of the cylinder. And this will happen just because with the rings running up and down, you're gonna get more wear up at the top. All the action happens, those power strokes and all that kind of, all the force happens when you're up there. So you get kind of a rounding out at the top as a result. So you're going to have an increased size at the top of the cylinder relative to the bottom of the cylinder. And if we want to talk about taper, the math is right here, A minus B. So you're going to take the bigger measurement, A, and subtract B, and it's just the difference in diameter. So we're not doing any kind of area calculations or anything. It's a very simple measurement. Taper equals A minus B. If you have excessive taper, you get to a kind of situation where you might have too much ring movement within the ring grooves, or a gap that forms, the ring gap gets too large. And as you get to the top, this is on the left here, a compression stroke. As you get to the top of the compression stroke where you have a lot of pressure going on, you're going to start to get blow by, which is not what you want. You want to keep all those gases in the chamber until you ignite and get to the power stroke. Likewise, if you are on the power stroke, which is the right illustration here, as you're driving down, that force is going to blow some of the gases by the piston rings, and that's not what you want either. So what you're going to get if you get that blow by, you might see a loss of compression, you're going to decrease your horsepower and your fuel economy, and you might even get some oil contamination from those gases. So enough talk, let's do some math. So we're looking at question 1 here. And if you want to find the taper and you're given an illustration or descriptions that is very easy, you know that your top measurement is A, your bottom measurement is B, your taper is simply A minus B. It's pretty intuitive, big number minus a smaller number. So if you do 8.76, make sure your two measurements are in the same unit. And you get 0.02, and because they went in as centimeters, they come out as centimeters. So that is the difference in diameter at point A and point B in the cylinder. In question 2, it's a little trickier. They're telling you the taper. So we know that if we do taper equals A minus B, our answer is on the left side. And the bore of 8.56 is at the top of the cylinder. So that means that 8.56, I'll just reuse this diagram, would be up here. So that's measurement A. So 0.02 equals 8.56 minus the bottom bore. And if you do that math, how can I get 0.02 from 8.56 if I do 8.56 minus 8.54? That's going to give me that taper. Check your math. So the bore at the bottom of the cylinder is 8.54 centimeters. Okay, the next measurement we're going to look at is out of round. And out of round, let's figure out where we are. So here we see a cylinder. We're looking down at it from above. So this is a deck. And we're kind of comparing the diameter or the bore of the cylinder in two directions, parallel to the crankshaft centerline and perpendicular to the crankshaft centerline. So bear with me while I draw something terrible. Say this is a crankshaft, little bearings, we have a piston, maybe we'll make the top a little round. And what the piston is doing as the crankshaft rotates in the cylinder, it's kind of slamming back and forth, perpendicular at 90 degrees to the crankshaft centerline. So that would be measurement C. So whenever you're calculating out of round, what you expect is to see the maximum wear at the top of the bore in a direction that is perpendicular to the crankshaft centerline. Okay, so that is measurement C. And if you are parallel to the crankshaft centerline, that's measurement D. And I expect to see less wear in that direction because I don't want my crankshaft shifting back and forth as I drive my car. That's not cool. So something that you need to know. I mean, if I give you two numbers, one is bigger, one is smaller, out of round is simply going to be the big number minus the smaller number. But if I give you a direction, you have to be able to understand where you would expect to see more wear in an out of round situation. So looking at some calculations for out of round, number one is pretty straightforward. I see a big number and a small number. The big number is C. The small number is D. Out of round. That's my out of round abbreviation equals C minus D. So in this case, we just take 8.73 centimeters. We subtract 8.69, and that gives me 0.04 centimeters, which is the out of round, or the difference in the bore / diameter, perpendicular versus parallel to the crankshaft direction. Okay, looking at number two, a little more complicated. They gave me the out of round. Once again, I have the left side of the equation. And now they've given me a bit more information. Oops, 1 second. Going back to number one, which direction to the crankshaft centerline? Direction of the smaller, because we do more wear perpendicular. Okay, back to number two. We are at a bore of 8.46 centimeters parallel to the crankshaft. So will be that be the direction with more or less wear? Less wear. Okay, that's going to be measurement D, parallel to the crankshaft. So we are looking for this. Okay, you can either just intuitively do it. You know that C's got to be bigger, so you're going to add that 0.015, or if you're feeling shaky, you can do a little bit of algebra. And then you're going to get your final answer, 8.475 centimeters, perpendicular to the crankshaft. More wear, bigger bore, perpendicular to the crankshaft. We're moving over to the camshaft now, what controls the valve lift in our engine. So we need to know what the lobe height is. So it's also called the lobe lift, and it's just the difference between the circle, the diameter of the normal thing plus, and the height of the lobe. So we're going to have measurement F here, also a diameter, that somehow missed it. And really just to figure out the difference between the maximum height of the lobe and, the minimum diameter, we're going to do E minus F, and that's going to give us this little piece in here as our unknown, the lobe lift. Super, super easy. Here I see the whole height with the lobe, and the base circle is 47.7. I subtract the diameter of the base circle, 38.1 millimeters, and I'm going to get my answer, 9.6 millimeters. Rocker arm ratio. So we're going to combine this with the lobe lift in a bit, but first we're just going to talk about the rocker arm ratio. So this is more for your cam and block engines. That's where you're going to see rocker arms happening. And if you look at the picture over on the right here, this is your typical setup. You would have your camshaft in your engine block. You'd have a lifter that is being affected by that lobe lift and lobe height. You travel through a push rod to this rocker arm. It's got a pivot point right here, so that's where it's attached, and it can go up and down like a seesaw basically, but a wonky one. So you're going to have a measurement between the push rod, which comes from the camshaft, so we call this the cam side, and the pivot point. And we're going to call that measurement X. It will always be the smaller measurement because you want to get a mechanical advantage from this. And then we're going to have a second measurement that goes from the pivot point over to where the valve contacts the rocker arm. And we're going to call that measurement Y. And it's going to be the bigger one. Here it is on another picture. Conveniently, it is flipped so that you understand that you have to look for that short measurement from the cam to the pivot point, the longer measurement from the pivot point to the valve. And this time, to find rocker arm ratio, we're using division. So you take the bigger number and you divide it by the smaller number to get the rocker arm ratio. Okay, so here's a couple of calculations. Number one, find the rocker arm ratio. So I see this picture, I see a big number and a small number. I know intuitively that over here I must have the cam, and on this side I must have the valve. I could call them X and Y, or Y and X, or I can just divide. So you're going to find the rocker arm ratio, another abbreviation, by taking the bigger number and dividing it by the smaller number. The answer to that math is 1.6. There's no units in this because it's a multiplier, right? So let's say, in a crazy world, your lobe lift on the camshaft was 1 centimeter. That means that your valve will open 1 times 1.6 or 1.6 centimeters, okay? We'll deal with that in a second. Let's just get another rocker arm measurement here. So number 2, how can I trick you by confusing you with fractions or confusing you with things that aren't intuitively obvious where the measurement is. So if I tell you the entire length of a rocker arm, I mean from valve side to cam side. Okay, that's one measurement. It's not that useful to me. I don't need that one for my calculation. Now I have the distance between the pivot point and the valve end is 1 3/4. So that means I got the long measurement given to me. So I have to do a couple of calculations here. First, I have to find out this distance so that I can use it in the division for the rocker arm ratio. Now, you can work in fractions. I know we've all learned how to do it, but most people hate them. So I'm just going to use decimals for this because it's more about the comprehension than the skills with your fractions. So we're going to change 2 5/8, the total length. I'm going to change that into decimal. I divide 5 by 8. It gives me 0.625. I add that to my whole number 2. 2.625. Same thing with 1 3/4. Divide 3 by 4, get 0.75, add it to 1. So there's my decimal form of those inch measurements. That's going to tell me that the distance between the cam side, the push rod side, and the pivot point is 0.875 inches, which if you did it in fractions is 7/8. Okay. Now, so I have my 2 measurements that I need to go into the formula. So that's my short measurement right here, and here is my long measurement. The rocker arm ratio is going to be 1.75 divided by 0.875 equals 2. Let's combine that rocker arm ratio with the lobe lift and lobe height calculation. So we have 2 situations that can arise. More commonly nowadays, we have overhead camshafts. So we have a situation where our cam lobe acts directly on the valve. So any valve lift, which is how much a valve opens right there, will be the same as a lobe height or the lobe lift. So you're just doing that distance here. But if you have an engine where you have a cam and block, where you're using a rocker arm and you're having that mechanical advantage, then you have to do a little more work. You have to find the lobe height or the lobe lift down here. And you have to find, sorry, what's a color that's going to show up on that? Maybe glitter down here. And then you're going to have to find the rocker arm ratio right here. And that's going to give you the valve lift. So let's see the math. Situation 1. We're going to lift an exhaust valve. We know the rocker arm ratio. We didn't have to calculate it. That's nice. And we know the lobe lift. So what we know when we know the lobe lift, just kind of harping on it, is we know this measurement here. And we know that we're going to amplify or, create that advantage. Valve lift equals rocker arm ratio times lobe lift or height. So we're going to take 1.65 and we're going to multiply it by 0.335. 0.553 inches. So even though our lobe lifts 0.335 inches, because of that advantage given by the rocker arm ratio, our valve is going to lift more. It's going to lift 0.553 inches. Looking at number 2, what is a valve lift of an overhead cam engine with a lobe lift of 0.342? Well, if it's an overhead cam engine, that cam's acting directly on the valve. So the valve lift will be the same as the lobe lift. All right, let's bring it all together. So here we have a list of either specifications or measurements, things that we're done. And maybe you're just geeking out on what your engine can do. Maybe you're thinking about modifications and you want to know what kind of improvements you're going to get, or maybe you are wondering if it's totally time to overhaul. These are all things you would measure. So I've listed a bunch of different measurements and I want to know some calculations. And we're just going to go start to finish. Blue, oh, is this blue? No, that's black. Let's try blue again. Blue is going to be our taper. So thinking back, taper compares the bore at the top and the bottom of a cylinder. So here's my bottom cylinder measurement, and I have 2 top of cylinder measurements. So we don't want to get into calculus. So we are just going to choose the more worn out measurement or the bigger measurement. So I've got 3.742 parallel to the crankshaft, or I've got 3.745 perpendicular to the crankshaft. This is a measurement I'm going to use for my taper. So calculation 1, the taper of that cylinder equals 3.745, the top minus the bottom, bigger minus little one, minus 3.738 inches. And that should give me a taper of 0.007 inches. Done. Moving on, out of round in red. So for out of round, I need to compare the bore at the top of the cylinder in 2 different directions, parallel and perpendicular to the crankshaft. So I'm going to use this measurement and this measurement. Out of round, big minus little, so we're going to do that 3.745, subtract the 3.742. Here we go, 0.003 inches. Next, lobe height is going to be green. We're going to compare the difference in cam lobe diameters from the base circle to when we have the long lobe. So we're going to compare these 2 measurements. Lobe height, big minus little, max minus min. I'm going to do that math and I should get 0.374 1.4 inches. Rocker arm ratio gets to be in lava pen. Okay, if I want to figure out the rocker arm ratio, what do I need to compare? Pivot point to the two sides. Valve side divided by cam side, or big divided by little. So we're going to take the rocker arm ratio, and we're going to take, remember we're switching from subtraction to division. 1.367, don't get on a tear with the subtraction. And that is going to give me 1.54. You can write it just like that, or you can do 1.54 to 1 as a ratio. It doesn't really matter. Okay, and lastly, in orange, yep, we're going to do the valve lift for this cylinder. So valve lift. Is the rocker arm ratio times the lobe height. Felt like I needed to write that formula down for some reason. So we're going to take that 1.54 and we're going to multiply it by the lobe height or lift. And that's going to give us a valve lift of 0.575 inches. There you go. There's all your general engine measurements.